full screen. Okay, this is the first hour of Physics 1B for December 6th, and today we're talking about sound waves. So we'll do a little description intro thing here, and say that a sound wave is a wave that travels through air, and in general, it's basically some kind of a pressure wave that expands out from a source, and the source usually is some type of, a voice or a speaker or something. And the one thing that all things that produce sound have in common is that they are all capable of creating vibrations in the air that can be sensed by your ear as small pressure fluctuations. So let's try to understand how it works. So let's start off by saying that sound is a longitudinal wave. I always find my handwriting is so bad when I first start using this because I only use this thing twice a week. Okay, so sound's a longitudinal wave. What does longitudinal mean? Longitudinal means that the velocity of the wave is parallel to the displacement of the medium, or to the displacement of the medium. And in the case of a sound wave, the medium is usually air, but it doesn't have to be. Sound waves can propagate through water, although if you and your friend go underneath the water in the ocean or in a pool and you try to talk to each other, you'll find that you can't really make out what they're saying very well. You can maybe read their lips, but the sound itself will sound muffled. Similar to the way that if you live in an apartment complex and someone next to you has like really loud speakers, you're going to hear their speakers through the wall, but they might sound kind of muffled and you might not be able to make out what it is, unless it's like music or something like that, in which case maybe you can make it out, but you probably couldn't understand voices. So sound can travel through walls, it can travel through metal, it can travel through really anything, but our ears are best at perceiving sound, or they're trained by our years of living to hear sound that goes through air, mostly. Okay, we will talk about sound waves and other stuff, but mostly we're going to be talking about sound waves in air. All the same ideas that we talk about still apply, whether we're talking about air or something else. Okay, over here on the left is a summary of the way we want to think about sound waves, but I'm going to start off by kind of trying to draw my own picture, and then we'll look at that as a kind of better example once we've understood what that picture's even trying to show. All right, so how do we get, so a wave, right, we said at the beginning requires two things. You have to have a medium, and then you have to have some kind of disturbance of the medium, right? So the medium we know is air. What does the disturbance look like? So imagine that we want to think about a one-dimensional sound wave, okay? Sound waves in general are going to go out in all directions, but let's just think about kind of a one-dimensional sound wave, because it's way easier to talk about the math in one dimension, and then we can always expand to multiple dimensions later once we understand what's going on. So for a one-dimensional sound wave, imagine that you have a, we're going to think of it as like a piston, since we've already studied gases. So say I have a chamber like this, and within it we have air. And let's say that at the end over here, I've got a little piston, and it doesn't have to be closed, but anyway. So we've got a little piston right here, and let's say that our piston is moving back and forth like this. So the piston is oscillating back and forth like this. This piston is going to be the analog of, in previous chapters for mechanical waves, a string, where someone is like oscillating a string up and down like this. It's causing waves on the string. So instead, if we want to produce a displacement that's parallel to the medium, we're going to need the object to slide back and forth like this instead of up and down, right? So this thing's moving back and forth. So what's that going to do? Well, it's probably going to send some kind of pressure fluctuations throughout the air. And the way that's maybe going to happen is that as this thing moves inwards, it's going to cause the sound, the air inside of here to kind of bunch up in this region here. So let's imagine that that's a representation of like really dense air caused by the fact that the piston on the other end was pushing inwards, and air is a kind of flexible substance in a way, similar to like a flexible cord or a trampoline, in the sense that it will, if you push against the air, it'll push back on you, right? So suppose that by pushing inwards here, you create a compression of air right here. This is going to be basically our disturbance that's going to propagate through the medium. Because again, that's one of the things that you're going to need to propagate a wave. And then what's going to happen is that because this region is slightly more compressed, as it moves through the air right here, as this piece moves backwards, it's going to create an area where there's less density. And so what's going to happen is that within the channel right here, as this thing moves back and forth, there's going to be these sections where the air is really dense, and there's going to be sections where the air is not so dense, okay? So in this section right here, the air is really dense, meaning slightly higher density than normal. And in this region right here, it's less dense. The word that you'll see used for that in different textbooks, although this word is very, I think, antiquated. I don't think it's used very much anymore. So rarefied, which just basically means not dense or less dense. Less dense. Maybe even low pressure, actually, is probably the better way to put it. If the density is lower, then the pressure is also lower. So the dense regions are going to be high pressure regions. Right? And yeah, the idea is that this whole kind of pattern of dense, less dense, or high pressure, low pressure, is going to basically move throughout the medium like this at some velocity v, and this velocity will be what we call the speed of sound in air. And that's kind of the idea. I don't think I drew that very well, but what happens next is, suppose that you're sitting over here, right, and you're listening to what's happening. Then what your ear does is it can detect really tiny pressure fluctuations in the air, and as a result, you can interpret this disturbance that's propagating through here as some type of a sound. So that's kind of how I guess I think about sound waves, and I think the book uses a similar kind of idea over here, which we'll look at here in a second. But does anyone have any questions so far? All right, if not, let's try to look at this picture right here. I can't really make it too much bigger because it's so long. Okay, so here's their version of what I'm trying to draw. Okay, so this is a sinusoidal longitudinal wave. Oh, and I should say that we can still define this wave using the same kind of equation that we used in the past. So in the past, we used this equation that was like y of x and t is equal to, what was it? You have the amplitude of the wave times the sine of, or the cosine, doesn't really matter, of cosine, the sine of kx minus omega t. We're going to use the same type of idea to talk about a sinusoidal longitudinal wave. So here we have a sinusoidal longitudinal wave traveling to the right in a fluid. And so here's a plunger, right? The plunger moves in SHM. What does SHM stand for? Do you all remember? Simple harmonic motion, that's right. So this thing oscillates back and forth in simple harmonic motion, so that means that it's going in and out, like this. And as a result, we have this kind of picture of what's occurring right here. So they're doing the same type of thing that I was trying to do over here, although their picture's a lot better, where they're saying that when this thing pushes in at a point that's t over 8, so this is the period, right? So 1 period will be the time that it takes to go from here down to here. And you can see if you were to trace a line through here that you get a nice little sine wave in terms of the way that this thing is operating, like that. So it pushes in, and then it kind of continues to push in, and then it starts to pull back. And the effect of that is that while it pushes in, it creates these dense locations here. In fact, the density, I think, or the high pressure part is getting more and more pressure as this thing gets further in. But then as soon as, this is the place where the thing starts to pull back, right? As soon as it pulls back, there's going to be kind of a less dense region here, a low pressure region. It pulls back even farther, and that low pressure region grows. Because now what's happened, I don't know if this part makes sense, is that you've sent a pulse out, right? Like this piece right here, which we can track as it began here and then it kind of grew and grew and grew into this large, really dense region. This piece right here is basically like a pulse, you know? And what's a pulse? A pulse is just a piece of a wave, right? What I'm thinking of is, as a way to compare this to something that's probably easier to physically see, because you can't see the air in the room when you're talking, right? Is if I have a rope, right? And I want to send a pulse down the rope. I want to do this one. Then the way that works is that you can just, with your hand over here, you can whip the rope, which will cause the rope to like lift up a little bit, right? And then when you whip the rope upwards, the effect is that it sends a pulse. So this is the pulse, right? Down with some speed in this direction here, right? Except this is a transversal transfer. By the way, you believe it's cosine. It actually makes no difference at all whether we put cosine or sine here, Troy, but if it makes you happier, I'll put a cosine here. I know the book likes to always use cosine, but you know, a cosine function, a sine function, depending on how you could shift the time by just a little bit and you get a sine function, right? Yeah, and it's kind of funny too that they always say sinusoidal instead of cosinusoidal, but that's of course because the word sinusoidal applies to any kind of a wave that fits cosine, sine, or whatever. Not tangents, though. Tangent doesn't work, right? Okay, anyway, so getting back to what I was saying, imagine you've got a rope, you hit it with a little pulse by whipping the rope a little bit. That pulse will then travel along the rope, right? You can try this with, go grab a hose or a long extension cord, or if you have a long piece of rope in your house, like for climbing or something like that, or whatever, or for just doing things. Obviously, there's probably lots of reasons people have ropes in their house. You can easily see this, right? So compare that to what's going on here. Here, the disturbance is created by the pushing of this piston, right? And by pushing that piston out, you eventually develop this high pressure region here. And that thing right there is the pulse, right? That's going to travel through your medium. And as long as you keep pushing back and forth on the end right here, you're going to keep generating these high pressure regions that are going to propagate down. And so you can see, like in the past, here's a previous high pressure region that was generated that's now traveling. Here's another previous high pressure region that's now traveling through the fluid, right? So the action of this pushing has created these pulses, right, that are traveling through your fluid here. And what are the pulses? The pulses are just these really high density, high pressure regions of the air, right? So this is high pressure, this is low pressure. All right. And then we can start to talk about some of the properties of the wave itself. And what they've done is they've identified these points at the center of these high pressure regions. And they're saying that if we look at one particle in the middle here and one particle in the middle here of the air, then those particles will stay about, one wavelength apart. And then they kind of track those particles. So the interesting thing here is for an individual particle of air, right, which is the medium itself, that particle is going to be part of a high pressure region. And after a little bit of time has passed, after 1/4 of a period, that same particle of air is now part of a low pressure region. And then eventually it'll become part, of a high pressure region, back again down here. Starting the process over again. Same thing with this one here. So the particles themselves are kind of doing this, right? And why are the particles oscillating back and forth like this? Because there's something forcing them to do that, right? This piston is forcing these particles to go in and out and in and out. And that is a really crude way of describing how it works, but that's really what sound is. And then, like I said, your ear is able to interpret these fluctuations. And now, if we want to understand the difference between the way sound sounds, like whether you have like a really high-pitched sound or a really low-pitched sound, what's going to depend on the wavelength, right? Because if the wavelength is what? Let's write the equation down. V is equal to lambda times f, right? Now, what does that mean? Why did I write it like that? That's not right. That's not right. V is equal, I said lambda times f, but I wrote lambda over f. Okay, I was trying to do the algebra in my head. So the frequency then is V over lambda, right? V over lambda. So if lambda is long, right, then the frequency will be low-pitched. And if lambda is short, the frequency will be really high-pitched. Okay, so how are these things determined then? What do you think determines the velocity of the wave? What do you know about the velocity, the speed of sound in air? Is it fixed? Does it change based on how fast you move this piece right here, this little piston? Or is it fixed? Okay, Troy thinks it's the force of the plunger. Astrolover thinks it's fixed. Does anyone know what the speed of sound in air is? Just off the top of your head, anyone know? 344. Okay, so it must be fixed if that's the case. If there's a number and more than one person already knows what it is, then that's probably kind of a hint that this is fixed. Okay, so this means that the speed of sound is a property of the medium, right? If we go back to think about how we found speed in previous chapters, when we talked about the speed of a wave on a string, the velocity of a wave on a string was related to the tension in the string. The more tense, the more tension, the more speed you get. And it's also related to how dense the string is, the mass per unit length, right? So sound waves are going to be similar. There's going to be a tension in the air, which is going to be related to what's called the bulk modulus. And then there's also going to be the density of the air, which is, just rho, the density of the air, which we also kind of know. So the speed is fixed. So that means that if the speed is fixed, if we want to get different frequencies of sounds, the only way to do it is to alter this thing right here, lambda. So if we come over to our picture here, if we want to get a wavelength that's really long, what could we do with our piston over here if we want to get a long wavelength to get like a deep sound? Slow piston cycles, yeah. So if we want to get a long wavelength, we want to make sure that the cycle here is slow. And in fact, you can see that the period that at which we're oscillating this is probably going to be related to the period of the wave, which is also related to the frequency. So if you want to have a low frequency, let's think about this. What is frequency equal to? Frequency is equal to 1 over t, right? So I think it's the opposite, Troy. Right? Because if we want to have... No, you're right. So low frequency would be long t, which would be slow. Long and slow mean the same thing, right? Okay, so that's right. The main point is this. I'm getting deep in the weeds here. The main point I'm trying to tell you is that the rate at which you move the plunger is going to affect the sound that's produced, right? And if we move this back over a long time scale, we're going to get low frequencies. If this thing is oscillating back and forth really quickly, then you're going to get high frequencies. And that should make sense because this is like going to be slow frequency, and then This would be like really fast frequencies. And that's going to change what we hear. So how do we connect this to actual sound that we hear and that we produce? So by some method, when you talk, there's a vibration that's occurring at the back of your throat that then travels through your mouth and then out into the world, right? So that thing that's happening at the back of your throat is the plunger, right? And it's effectively sending like a vibration in the back of your throat that will push on the air, that will then come out of your mouth and then kind of echo through the room, right? And that's how we produce sound. Of course, we don't think about that. We don't think about the fact that there's some kind of plunger in the back of our throat that's moving like this, but we intuitively understand how to change the pitch of our voice, right? Especially people that are really musically talented and people that have like really good singing voices where they can really control the pitch of the sound that they produce so that they can sing in key, so that they can make sure that they don't sound out of tune. Right. But we all are able, right, to change the frequency of our voice to go from really high pitches to much lower pitches. We just kind of naturally know how to do it, right? We don't understand. I mean, you learn how to speak long before you learn this equation, right? And you don't need to know that the velocity of sound in air is fixed. You don't need to know anything about the physics at all if you want to actually use your sound box inside of your mouth to make sounds, right? What's the name of it? What is the thing that actually produces those vibrations? Does anyone know? Is it our larynx? Is it our voice box? What's it called? It's been a long time since I studied biology. How are we doing on time? Sometimes this kind of stuff I can take wherever. We're doing okay. Is it a diaphragm? So your diaphragm is down here, right? And you're like toward the base of your... It is larynx, right? I think it's larynx. But, I'm sure that the way that our larynx works is much more complex than what I'm describing over here on the left, or whatever it is in our mouth that's actually producing these fluctuations. But one way you can compare this to something that maybe you've seen before, if you look at a speaker, right? So let's say you have a speaker. Speakers usually have this feature where there's kind of like a circular thing here, and this, you might not see this on all speakers because they may be covered with some kind of a net or something, so you can't see it. But there's usually some kind of like something like this when you look at a speaker, and if you turn it sideways so that you're looking at your speaker like this, then there's usually kind of a cavity right here where it kind of goes in like this. But then there's usually some kind of a, what I should really do is just go to the internet and get a picture of a speaker here. But, so I'm trying to draw a speaker. So imagine in your mind a speaker, if my picture doesn't, and there's this little piece here that when the speaker is operating, this little piece basically vibrates in and out, right? And that's actually what produces the fluctuations like over here that produce like the sound that we hear, right? Is that something you all have seen before? You saw it many times when you were a child, yeah. Let's here, let me go to the internet real quick and just find a picture of a speaker, just to speakers that could mean anything. Let's see if it actually pulls the right stuff up. Yeah, it did. Okay. So if we go to images, yeah, so this is like the piece this is like the active piece of any speaker, is you have this little piece in the middle that basically vibrates up and down. And does anyone know how it does it? How do we take music from a computer or from, a phone or whatever? Let's say you plug it into a speaker. What does the speaker actively use to make this thing vibrate up and down? Does anyone know? And you can see all of them have this same feature, right? They have this big circular thing that's flexible. It can vibrate in and out. All of them have it. And I believe that in the case of things like this one here, I think these bigger ones, I get you wrong about this, I think these bigger ones here produce the really low bass sounds, and the smaller piece here produces the really high treble sounds. In fact, I don't know, the speaker system I have in my house, I've got a bunch of little ones that have this piece, then I have one big subwoofer. You assume it's electricity and a spring. Definitely a spring involved, and it's, electricity is, yeah, it involves electricity and magnetism. There's a magnet inside of these things, and they basically can oscillate up and down. Anyway, so that is kind of an intro to sound and our understanding of the way that it's produced. Without going into too many technical details about what's happening, we think that sound is a longitudinal wave of pressure, sometimes just called a pressure wave. And this is our picture. And the idea is that you just need to have something that can create a disturbance. And it could be a string of a guitar, it could be a speaker, it could be a piano, it could be your voice. Any of these things can produce these vibrations that we're going to try to understand today. Okay, anyone have any questions or comments about experiences they've had or anything like that? Okay, so it's important to understand now, or to ask, what does this even mean now? So when we talked about a mechanical wave, we could understand that up and down was y, and left and right was x, right? And then time just proceeds. So it made sense to have an equation like this. Well, now our y probably that's probably not a good variable to use anymore. So instead, and your book doesn't do this, but I think I prefer this. Let's say we make it s. The point is that now for our wave, we need this to be a longitudinal wave. It can't oscillate up and down like this. It has to oscillate left and right. So S now is going to have to represent something about the displacement of the particle. And in this picture right here, S could be the distance away from equilibrium for our particle. So for example, we could say, let's say that this point right here is the equilibrium position of our particle, right? And the particle moves to the left, right? And then it moves to the right. So you could say maybe when it moves to the left, it has a negative displacement. When it moves to the right, it has a positive displacement. But what you'd have to do is you'd have to kind of like draw a line down here and say this is s equal to 0. And then, you know, this could be right here. This would be negative a. So this would be s equal to negative a. And then down here, where's the maximum? Right here, this would be the maximum. This would be s equal to positive a. And then you still produce the same kind of sine wave that you can see here. But now s is actually kind of measured in the same direction as x is. So x is in this direction, but x increases forever. The s values are going to be relative points within the medium, kind of like this right here. So each individual particle is going to have its own like s coordinate system in a way. Anyway, we'll develop this. We will talk about how we can write the pressure as a function of time, but we're going to start with this as our understanding of it, okay? And then we're going to try to build a sound wave. Oh, they use S in this one too, I forgot. We're going to change their, why do they do it cross-sectional area S? They've never done that. They always do cross-sectional area A. We're going to change that. We're going to fix this picture here because this seems stupid. We're going to make this an A. The cross-sectional area A. There we go. That way we can still use S here as another kind of. Okay. We're gonna have to change all these variables. We'll have to just draw our own picture, I guess. Okay, so that's what we want to talk about now. Is how is sound a pressure wave? Because that's something that people say all the time. And if it is a pressure wave, can we actually write down a wave equation? That's what we want to answer. We want to have a wave equation. Put this down. for sound. I'm not going to be able to just not leave that there. I hate the fact that they use Y. I just can't deal with it. We're going to have to draw our own picture. Okay, so we're going to think of this as this is right here. So as a sound wave propagates along the x-axis, the left and right ends undergo different displacements y1 and y2. So let's see if we can look at this picture and understand what they're saying right here. So here I have undisturbed cylinder of a fluid. So the fluid could be air, for example, that has cross-sectional area A and length delta x. So there's the length. The area is on this end right here. And then volume would be, this would be A times delta x. It says a sound wave displaces the left end of the cylinder by y1 equal to y of x and t, and the right end of the cylinder by y2 equal to x plus x times delta t. So for our variables here, we're going to be saying that S1 is going to be equal to S of x and t. And again, just rewriting our equation up here. So S of x and t has to be, was it A cosine of kx minus omega t? Okay, so, and then S2, another point in the fluid, is going to be S of x plus delta x, because we're at a new position of the fluid. Oops. But then also at the same time t. Okay. So how is this happening? A sound wave displaces the left, so the undisturbed cylinder of fluid is this little blue thing right here, right? And I think what it's saying is that the sound wave displaces the left end to here. So the left end was over here, but now it's been displaced by over to here, right? And the right end, which was originally here, has now been displaced all the way to here. So the sound wave has effectively taken our tube of fluid and it's effectively stretched it out a little bit. Does that make any sense? How does that compare to our picture up here? So the sound wave is coming from this thing that's oscillating back and forth right here. And it has the effect of pushing on the fluid. And I think what we're saying is, so imagine some force came in this direction here and pushed on our fluid. It would push the fluid forward, but we're saying it's also going to cause the fluid to, it looks like it expands, right? Does it look like to you that it expands? What do you all think? Definitely the front of it moves from here to here, right? The front was here, and now it's here, the left edge. And the right edge, which was right here, has now been pushed to here. But it looks like the whole thing has expanded, right? Okay. All right. So, all right. So what can we say has happened now? We can say that our fluid has expanded a little bit. By an amount that we're going to call the change in volume. So delta volume. I'll just call it delta V, but the delta volume, change in volume. And it should be equal to, well, so the original volume was A times delta X, right? The new volume, what's that going to be? Is it going to be y2 minus y1? The change in volume. So they're saying it's this. They're saying that it's equal to the area times, using our variables, S2 minus S1. That seems like that's just the new volume, right? If we write it down like that, Here, wait, do you all understand this? Why would this be the change in volume? What do you all think? Why would it be area times S2 minus S1? I'm going to read through this so we can understand what's happening. It says, when a wave is present, at time t, the end of the shaded volume in the figure... Wait, I skipped something. When a wave is present, at time t, the end of the cylinder that is initially at x is displaced by y1. Okay, we got that right. That makes sense, right? The cylinder started here, and it shifted to here. When a wave is present, the cylinder that is initially at x is displaced by y1, and the end that is initially at x plus delta x is displaced by y2. This is shown by the red lines. If y2 is greater than y1, as shown, the cylinder's volume has increased, which is what we said, which causes a decrease in pressure. That makes sense, because if the volume gets bigger, the pressure has to go down. If y2 is less than y1, the cylinder's volume is decreased and the pressure is decreased. And if y2 is equal to y1, then the cylinder simply shifted to the left or right. There's no volume change, no pressure fluctuation. The pressure fluctuation depends on the difference between the displacements of neighboring points in the medium. And it says that the change in volume should be equal to this quantity here. Why would that be the case? So y1 is the distance that the left end has been displaced. And y2 is the distance that the right end has been displaced. So the new volume, wouldn't the new volume just be equal to this? Oh wait, how are these things measured? That's the thing that's so weird about this. So y1 for us is S1. So this is S1. This is S2. Sorry for changing the variables. It's just the y thing was bothering me. So if this is measured relative to where the particle was to begin with, so that's this distance here, and this is measured relative to where the particle was to begin with, so that's this distance here, I think I understand why it's saying that then. Because now, yeah, because this tells you how much the first particle moved over. This tells you how much the second particle moved over. We can see that the particle on the right side, whoops, moved more than the particle on the left side, which is why the volume got bigger, is because the one on the right is bigger than the one on the left. So this actually does make sense to me. The question is, does it make sense to you? It's less important if it makes sense to me. It's more important if it makes sense to you. Does this make sense? What do you all think? So the S represents the amount of displacement that the gas cylinder underwent, right? And the left end moved to the right by some distance S1. The right end moved to the right by some distance S2. Now, if S2 was equal to S1, what would the change in volume be? 0. That makes sense, right? Hopefully that part makes sense, because if the left, so if it was like a particle, particle can't happen. For a particle, it would always be the case that if I take a single particle, like let's take our pen, if it moves through the air in this direction, then the distance that the left edge moves is the same as the distance the right edge moves, which means that means this thing didn't get compressed as it moved. But air is different. Air can be stretched and compressed. So if the right edge gets bigger by some amount, and the left edge gets bigger by some amount, then if you take the difference between those two, you'll figure out exactly how much the volume has changed. That does actually make sense. Okay, is everyone on board with that? If the right edge goes farther than the left edge went, then the difference is how much the thing actually got bigger in that dimension. Okay, I'm on board with this. Are you all on board as well? Any questions so far? If you flat out just don't understand something, you can just say, I don't understand. And I'll try to explain more. Doesn't mean that I'll be able to explain it in a way you understand, but I can try. I can try a different way. Maybe draw another picture. You're still confused. Okay, let's see if we can draw our own picture and see if that helps. So we start off with this packet of fluid, right? And it has a kind of a fixed size to it, but so here's our fluid, right? Now, through some method, maybe because we put a piston here or something like that and we push on it. Right, yeah, I agree with you, Matthew. So, some kind of force comes along, right? Now, as a result of that force coming along, our fluid moves. So our fluid is now not only going to move, but we're going to assume that it gets larger at the same time, right? So here's our second picture of our fluid. This packet of fluid, we'll call it fluid prime. Now, we're going to say that the cross-section, it doesn't look like it, but we're going to say the same cross-sectional area in both cases. I know it doesn't look like it. Oh, what we can do actually, to be really exact about this, we can use technology instead of using my primitive digits, and we can just copy paste and say, okay, our fluid, which was originally there, right, it's now moved to the right, and in this case it hasn't stretched at all, but what we can do is we can just stretch it, right? And so now here's our fluid a little bit later, right? So our packet of fluid has now moved to the right. So now what we want to come up with a way of doing is figuring out how do we define how much the volume's changed, okay? And one way we could do that is say, well, what we want to do is we want to track how far the left edge moved, right? And the left edge moved some distance that we're going to call S sub 1. And we want to track how far the right edge moved as well. And so we come over here and we say, okay, well, the right edge appears to have moved from here over to here, which is now S2. And we can see that S2 is definitely greater than S1, right? So now how do we go from that to this? Well, if we want to know how big each of these objects are, what we would need is another dimension on here, okay? So let's say that I call this length right here L, and I call the new length L prime, right? And we have our cross-sectional area, right? So our initial volume would just be A times L then, right? This, I think, is what's missing from this picture that's making this really hard to understand. And then our final volume, which is down here, right, would be equal to A times L prime, right? You're all on board. This part's easy to understand, right? Initial volume, final volume. That part's easy. Okay, so then how do we get to the next part? Well, there must be some way to just say that there's a connection, and I think we can do this. It might not work out. Sometimes that's just how it works. So now what we want to find is VF minus V initial, which we can see is just A times final L prime minus L. And presumably we're going to be able to prove that these are the same, and it shouldn't be too hard. What we can see from our picture here is if I take L plus S2, can anyone tell me what that's equal to in terms of the other two variables? What's L plus S2 equal to? So L plus S2 is, this is L, this is S2. What's L plus S2 going to be equal to? S1 plus L prime, yeah. So all we've done there is just say this whole length is some distance. Call it Q or something. Q is equal to this plus this, or it's equal to this plus this. And now it should just take one line of algebra. So move the L to the right-hand side, we get L prime minus L over here. Move the S1 to the left side, you get S2 minus... it worked. That's good. That's good when things work out. But they have to. I mean, it had to work. So that's how we get from this back up to there. Is everyone on board? Does that make sense? Okay. Yeah, it's really hard to see from their picture because they didn't give us... You can see delta x here, right? But what's missing is this distance here, and then it would have been really easy to see. All right. Maybe I really shouldn't just use their pictures. I don't know. Anyway, at some point in time, you're going to have to go back
I know not all of you will do this, but I know some people will. You'll go back at some point in time and you'll reread these textbooks. And so I want to have a way that you can connect what we do in class back to what you're going to read later on, just so you have a reference point in case you ever need to. Okay, so let's start from here then. I don't have to keep all this stuff on the screen, right? We can just shove it over there. Okay, and then it's still on the notes, but all right. So we have this, and we had said that S1 is going to be our S of x and t, and S2 is going to be our S of x plus delta x and t, because x plus delta x represents the right edge of the thing, and x represents the left edge of our fluid. So what we can do now is we can write out what this is equal to. So this is equal to area times, so S2 is S of x plus delta x comma t, and then S2, so minus, that's S2. S1 is S of x and t. Okay, there we go. And now what we're going to do is we're going to look at the change in volume divided by the initial volume. Okay, so we're going to write delta V over the volume. And this is going to then be equal to all of this that we just wrote down. Remembering that our S of x and t, right, is this. Actually, let's do this first. Stop it. Copy, paste. We're going to need that in a second. So remember that this is how the piece of the medium is moving as a cosine function. And this, of course, comes back to this thing. That's why it's moving like this. It's this thing on the edge that's shifting back and forth. So delta V over V, the change in volume over its original volume then, is going to be area times divided by our initial volume, which was just, I think, A times delta x, right? A delta x. And now what we're going to do is we're going to take the limit as delta x goes to 0. Make a little space here. I'll write it like this. So now, if we take the limit as x goes to 0, our volume is going to become infinitesimally small. So we'll call that dv now. And we take the limit as delta x goes to 0. Your book loves to do this. It's interesting I'm doing this today because I'm going to be doing the same thing in my, almost the same derivation is going to show up today in my E&M class for deriving the equation for an electromagnetic wave, a light wave. Because of course it is. Sound waves, light waves, they're all basically the same thing. They're all waves, right? So it makes sense we would have a very similar type of derivation. Okay, so what do we do here? All I've done is we defined our change in volume. We figured out where that came from. And then we defined our change in volume over the total volume, the initial volume. And the next step we do is let's take the limit as delta x goes to 0. As delta x becomes very small, that means that this displacement here, this is very small. The size of our fluid that we're considering is going to get smaller and smaller and smaller until we're just thinking of like a sliver of fluid that contains just a few air molecules inside of it. And they're just oscillating around like this. So if the delta x goes to 0, that's going to become dv on the left-hand side, and we're going to get the change in volume over the volume. And that's all equal to this. But if you look at this, you can see that the areas cancel. So we don't really need these anymore. What is that equal to? The limit as delta x goes to 0 of some function s of x plus delta x comma t minus the same function evaluated at another position x comma t, and then we divide by delta x. What is this whole thing equal to? Does this look familiar to you? You ever seen that in your math class? It's the derivative. Yeah, it's the derivative. That is the derivative. This is the formal definition of what a derivative is using limits. And it's one of those things where you may have seen this in like pre-calc, or you saw it like the first few weeks of calculus, maybe when we were talking about limits, but this is the same thing as it's actually a partial.
It's partial derivative because this is a function that has two variables. This is going to be the partial derivative of s with respect to x. So now we know that dv over v is equal to the partial of s with respect to x. Partial derivative, right? Okay. So the next thing we need to do is we're going to go back to something that I don't know if you all studied this in your physics classes. This is something where, like, I know I cover it in my physics class, but we often, because physics 1A is so incredibly dense and just thick with material, this topic is often skipped. So I'm going to show you where this next part comes from. So chapter 11 is on equilibrium and elasticity. Probably when you studied this chapter, you spent a lot of time dealing with the conditions of equilibrium. You all remember this stuff? Net force equal to 0, net torque equal to 0, stuff like that. But also, deep within this chapter that covers all this other stuff that mostly gets focused around solving, if you guys remember these kind of problems, stuff like this, where you've got, like, will the ladder slip? But there's buried at the very back of this chapter, something that people often don't cover, is stress, strain, and elastic moduli. And I know in this class, you've all probably had to reference this chapter at some point, right? But they talk about tensile stress, and they come up with this thing called Young's modulus. We're going to need to use this here in a second. So just Young's modulus involves when you try to stretch something. This is like you take a cord and you try to stretch it, or if you take a piece of metal and you try to, like, pull on both ends of the metal and stretch it out. The metal's going to resist, and the amount by which it resists is going to be related to something called Young's modulus, which is tensile stress over strain. Stress over strain is the theme of this particular part, and this is something that we can look up in a table. It's also related to a bunch of other stuff over here, but Young's modulus, bulk modulus, shear modulus, this is the piece that we're going to want to understand here. So aluminum, brass, copper, iron, lead, different materials have different values for these things. That is to say that aluminum is easier to stretch than nickel. Rubber is much easier to stretch than any of these because the Young's modulus is 0. That's all that this means, is how stretchable are these materials. The bulk modulus represents how much you can compress the material or stretch the material, okay? And that's the part we're going to be using now. So bulk stress and strain is related to pressure, and here's the equation we want. Notice there's the delta V over V that we just talked about, right? So this is our equation. It says that bulk modulus, and here's some, bulk modulus is equal to the negative of delta P, the change in pressure, over the change in volume divided by the initial volume, right? That's what we need. So let's write that equation down. So we have, from chapter 11, we have that bulk modulus B is equal to the negative of the change in pressure divided by the change in volume divided by the initial volume. Did we get it right? It looks right to me. And again, here's a picture over here so we can understand a little bit about what's going on. We have an object with an initial volume of V. It's put under bulk stress, which is to say that there's some pressure that's exerted on from all sides, right? Indicated by force in all directions. That pressure is going to tend to want to collapse this object, and the amount that it will collapse, the amount that its volume can change, is going to depend upon how much pressure you put on it and this thing called the bulk modulus. Okay? So, what we're going to do is we're going to understand that when we talk about sound, which is what this is all getting back to, when we think about this pressure wave of sound, our ears sense variations in pressure in the air. So the delta P is effectively going to be what our new pressure is. So I'm going to take this equation and we're going to rewrite it like this. We're going to say, I guess we can call it delta P. We can just remove the delta later, right? So delta P then appears to be equal to negative bulk modulus. I want to say buoyant force all the time, but bulk modulus, this is again just a number in a table for different materials, multiplied by delta V over V. So what we have is, well, we just found that delta V over V is del S del X, right? So our change in pressure is going to be equal to negative B, and then instead of delta V over V, we'll just replace it with dV over V. We just have a del S del X.
By the way, why is there a negative sign here? Let's look at this equation. Why is it negative? When the pressure is going up, what happens to the volume? If I increase pressure, volume goes down, right? So delta V would be negative, right? So when pressure is big, change in volume is, it's getting smaller. That's where the negative sign comes from. Okay, so we got this, and we have this, right? So what's del S del X equal to? Let's do that next. Let's look at our equation here. It says S of x and t is a cosine kx minus omega t. In order to find the partial of S, this function, with respect to x, what we do is we just take the derivative as we normally would, but we're only taking the derivative with respect to x, and everything else in the equation is a constant. So if we do that in our equation here, we're going to have the derivative of the cosine function is negative sine, right? So we'll have negative a, and then I'll leave some space, times the sine of kx minus omega t, and then I need to do the chain rule. I need to multiply by the derivative of the inside. So the inside function is kx minus omega t, but this part is a constant, right? Because we're taking a partial derivative. So when we take the partial with respect to x, we're only going to pull out the k, the wave number for the particle. Okay? So our equation for the change in pressure is going to be negative times, so I'll not skip steps, negative b times negative a times k times the sine of kx minus omega t. And then we get that the change in pressure as a function of x in time is just equal to negative negative, right? So we get b k a sine of kx minus omega t, where we can now see from this piece right here that the maximum pressure, the maximum change in pressure, is going to be given by b times k times a, where b is the bulk modulus, which basically tells you how flexible the medium itself is. So something like air is way more flexible than steel, for example. K, right, is just wave number, right? Just to remind you, k is equal to 2 pi divided by lambda. And then A is amplitude. This is just the displacement amplitude. This is going to be whatever the maximum kind of back and forth motion of our particles is within the medium. Remember that A was this, which means that it represents the distance that the particles move maximum, right? In our picture, the particles move the distance of this distance on the left side and this distance on the right-hand side, but there is a maximum distance the particles could have moved, and that's what the amplitude represents. Anyway, so this is how we can say that sound is a pressure wave, right? Is because it's the pressure itself that's varying here. The pressure is varying, and it's that change in pressure that we actually interpret. Your book gets rid of this delta sign. I'm going to leave it on there because it's important to understand that it's not, it's a change in pressure. In fact, it's a change in pressure above atmospheric pressure. So one of the easiest ways to measure this is to refer to it as gauge pressure, because then it's all about how much did it change above or below atmospheric pressure, right? One thing that we might need is to, so there's a few different substances here, but going back to this one here, there's not a lot on this list. Maybe this is the kind of thing we have to look up on the internet at some point. I don't know. But bulk modulus, right? It's just keep in mind that this is something that exists in a table that you can go grab for when you're doing your homework problems. And this is in chapter 11. Okay, so getting back to what we were doing. What time is it now? We have time to do a problem? No, we went way over. Well, so we got to that point. I guess it's a good place to stop, and then we'll just do some problems. So the first problem we're going to do is this one, and then we're going to do this one. I'll maybe put it so you can see both of them on the screen. Maybe if you want to, you could try to do the problem during the break, but we're going to take a break for 10 minutes, which which will be something like 1101.